Yeah, actually, that's right. So I think since I'm one of the organizers, I'll actually take the opportunity to thank all the speakers and all of you for attending. It's been a lot of fun to hear the wide range of perspectives and topics this week. And of course, also thanks to the Simons Institute for hosting us. The date I noticed is wrong here. Actually, obviously, it's November 20th, not October 20th. I haven't been sleeping much lately. So I'm going to, I think in the interest of time, I'm going to skip over some of the introductory material here. We've heard a lot about ride-sharing platforms already, so let me just skip that. I think at this point in the week, between the talk that was given by Chris Nosko on Monday and then also the Industrial Visitors Day we had last week, we all are familiar with Uber and Lyft and Sidecar and platforms like this. So what's our goal in our work? Oh, and I should actually, preface this by saying this is joint work with Sid Banerjee, who's an assistant professor at Cornell. He was doing a postdoc with me, and Carlos Recalme, who's a student of mine at Stanford. And also Sid did an internship with Lyft with their data science team. And so some of the inspiration for this work came from talking and working with them. So I guess what I'm interested in getting across to you and what I found exciting about this problem is that there was a combination of maybe three things that we needed to somehow include in one model and then use that to actually say something useful about the strategy that the platform takes. And that's basically that there's passengers and drivers who are strategic. The platform is setting a pricing rule, a decision for how transaction prices are set on each interaction. And then there's this kind of underlying queuing dynamic that governs the number of rides that are requested and the number of drivers that are available. And in isolation, we have a lot of different models in various literatures that tell us about any one of these three problems. One of the things that makes this really interesting to me is the fact that all three kind of come together in one place. So this would just be, I think, a pure theoretical exercise. It would be fun to build a model of something like that. Now, of course, you want to do that with some purpose in mind. In our case, the motivation for wanting to do this in the first place is that we sort of wanted to try to understand what the advantages were of using a dynamic pricing policy over a static pricing policy. And I'll explain more what I mean by that as we go on. So I'll skip this slide as well. I just want to briefly point out that there's a wide range of literature in very different communities, actually, that touches on this. So at the same time that we've been thinking about matching markets, whether in econ or in the EC community, it's been interesting to see in the applied probability community, there's been a huge surge of interest in models of queuing systems with matching behavior. And so I think, for those of you that are working on matching markets, I would strongly recommend sort of looking into some of the work that I think really starts with Adon and Weiss and goes from there. There's a lot of work on strategic queuing models, two-sided platforms, revenue management. So, like I said, there's a lot there, and one of the things that made this fun is sitting at an intersection of those topics. Okay, so let me tell you a bit about the model. So the model is something where we need to capture three features. So one is that I need to be able to say something about the platform's goals. How is it setting a pricing policy? I need to be able to tell you what the incentives are of passengers and what the incentives are of drivers, and that's all sort of the strategic aspect of the model. I also want to be able to tell you, exactly, even fixing all of this, how does the system evolve? What are the dynamics of drivers and passengers? Okay. So an apology I want to interject here is that I think this is a talk I personally view as sort of at the tip of a very large iceberg. And in many ways, I think the work that we were doing raises more questions than it answers. So I'm happy with some of the answers we got. But I also want to be very kind of explicit with you where I think there's important things missing. Okay? So some of them are on this slide, and some of them I'll mention as we go through. So one of them is that we're going to focus on just a single block of time. And what do I mean by a block? I mean something like, let's say, rush hour. Or maybe for those of you that were here for Chris Nosko's talk, a block of time might be a window of time around when bars close on a Friday or Saturday evening. So why is that important? In many ways, what I want to focus on here is not I want to avoid talking about predictable changes in demand. Okay, so everybody knows there's going to be more demand around rush hour than there is in the afternoon, right? So I want to avoid that. And indeed, the platforms avoid that. So even before surge pricing became sort of something which is changing at a minute-to-minute basis, it was the case that they would know in advance that there's going to be greater demand, let's say, around rush hour or bars closing, and the surge multiplier would be higher in those intervals. So when I talk about static pricing, I don't mean a fixed price over the entire week. I mean static over something like a few hours, a block of time. Okay, The next thing is in the talk, I'm only going to focus on a single region. Now, of course, cities are not just a single region, and I think even Chris on Monday mentioned that the pricing involves multiple neighborhoods. In the work that we've done in the paper, we do have the main insights that we have do generalize to networks. There's some sort of exceptions to that, but I'm not going to dwell on that in the talk. I think one important problem that my focusing on a single region completely ignores, and even the work on networks completely ignores, is, I guess there's two issues that sort of eliminates, right? So one is the notion of an estimated time arrival, or ETA. And I think, as you heard from Chris, and as anyone who actually uses Uber or Lyft would know, in addition to whether or not they're surge pricing, you're very sensitive to when you think you're actually going to get a ride, to what the ETA actually is. So sort of by fixing the network, and you'll see more in the model sort of how this plays out, one of the things we don't actually have much to say about is how passengers are sensitive to ETAs, and sort of, in particular, one thing that might mean is that the design of the regions themselves, like what you consider to be a region, is not a topic that we address at all. Right? So you may want to make your regions more granular, so that you're able to better, acclimatize, better match supply and demand on a very local scale. But as you do that, you will also want to make sure that drivers who are nearby are able to move in or out. Okay, so we're not really accounting for those effects in the kinds of network model that we build. And I think so thinking about ETAs and how the platform actually designs its topology. I think that's a really interesting direction of work. It's something Sid and I have talked about. We haven't really done much with it yet. And finally, the last thing I'll mention is the objective function I'm going to focus on is throughput, the rate of completed rides. There's at least three objectives that you might care about. There's throughput, there's profit, and then there's welfare. So we have results for throughput that sort of have no qualification whatsoever. We have results for profit when the system is supply limited, in a sense I'll make precise. And then there's similar numerical results for welfare, but the theory there is actually a bit more challenging, and so I'm not going to claim anything for that in the talk. Okay? So let me start by modeling sort of the strategic side of the problem. And this is another point which we'd say very little about. We don't say anything in our paper on, and I think it's an interesting issue, is that we're going to just assert that the platform takes a fixed fraction of every dollar that's spent. And I think that's fairly consistent with how the platforms work today. But it's kind of interesting. I mean, as a mechanism designer, you might actually think this is one of the very first things you would want to design, you'd want to optimize over. So our work does not optimize over this. It kind of holds that as an exogenous constant. I think one of the most interesting things to do is to kind of, and a lot of questions during Chris's talk on Monday, I think, alluded to this, that it's interesting to think about whether the platform should be sort of varying the share that it takes, perhaps, based on the state of the system. There's good reasons why most platforms don't really change this on a very fast time scale. I mean, this is the type of thing that would be updated, over months or something like that, if at all. And it's really I think it's more of a sort of cultural issue, right? I mean, I think drivers and passengers would not be very happy if they kind of were subject to a rapidly varying share of earnings. It becomes very unpredictable from their perspective. Of course, the platform needs both drivers and passengers, and it uses pricing to align the two sides. One note on terminology. In the platform's literature, in economics, if you use the word pricing, you have to be a little clear what you mean. So pricing might mean the fee structure, which is the gamma here, for example, or pricing might mean actually setting the transaction price. And one of the reasons that ride-sharing platforms were fun to think about, in contrast to other kinds of platforms that I find interesting, is because they actually directly set the transaction price. So that's why this is an interesting question. If you compare that with something like, let's say, Upwork or Airbnb, they have a lot of influence on what the transaction prices might be like, but they don't actually directly set them. Okay, so here when I use the word pricing, I actually mean the platform is setting the transaction price. And so they're able to use their mechanism for setting the transaction price to align the two sides. So the first bit of notation is that the way I'm going to model the platform setting the transaction price is just as a function of the number of available drivers. Remember, I'm focused on only one region. So there's a number of available drivers right now in that region. I'll imagine there's some function that the platform uses to map the number of available drivers to the price that you're going to get charged if you take a ride right now. Okay. All right, next qualifier. So when I say price, I'm saying you're setting the transaction price. And again, it's not directly the transaction price that's being set in the ride-sharing platforms. It's a multiplier on the on a base price. Okay. So the way these platforms work, they'll have a published formula that's time and distance dependent that's on their website. And if you use a fare estimator, you can actually directly calculate this. So that's what they call the base price. And any price manipulation that's happening on a faster time scale is happening through a multiplier. So Lyft calls it prime time pricing, Uber calls it surge pricing. And so what's happening is that they will tell you that there's some percentage that's going to get added on top of the base price because of the sort of current state of the market. So when I use the word price in the talk, what I'm really talking about is this multiplier. Okay, that raises yet another interesting question, which is, of course, Los Angeles and San Francisco are very different markets. And in Los Angeles in particular, there may be a very large cost to pulling drivers from, that look available from further away to come pick up a ride. And that ride, that cost is partly distance dependent. So these kinds of things, it's often a question that comes up here is, well, why is this also not a matter of manipulation? Not just a multiplier on top of a formula, but why not actually just directly be sort of manipulating prices in a way that you're not just picking a single multiplier regardless of what the time or the distance is going to be. And again, something I'm not touching. I think this is another one of those things, just thinking about from a regulatory perspective, ride-sharing platforms are fighting against the taxi industry, and that's, the taxi sort of industry has, published fare schedules like this. It's already challenging enough to convince the public that, surge pricing or prime time pricing is palatable. I find that shocking, I have to confess, but that's the way it is. So given that that's hard enough, I think varying this is also going to be politically even more difficult. But that said, from a market design standpoint, I think it's a reasonable question to ask. Okay, so that's the platform. Yeah.
So just in regards to how you set the price on the
multiplier.
No, actually, so your previous slide.
Yeah.
It was just depending on the
number of available drivers. Yes, I'm going to have a model where the state of the system is the number of available drivers.
So it's the way to think about what might be left by that is that when there were 0 available drivers, you might imagine that I would also want to use how many people are trying to find a ride, and this doesn't let me.
Yeah, and this doesn't do that. That's right. Yeah, so I think there's a lot of different things that are being left out here. So that's part of it. And as you're going to see in a second, I'm taking in my talk an extreme view where drivers are making entry decisions over longer time scales. And now, if you think about some of the tools that platforms are using, and Chris talked about some of these on Monday, another thing that's left out here is not just sort of the number of available drivers right now, but let's say a forecast that I have of how many available drivers there will be. All that kind of stuff is just left out of a model like this. I think there's a lot of interesting things to do there in terms of the richness of the pricing policy. Okay, so with the passengers, what do passengers do? Actually, fairly simple model of passengers. Every passenger is one ride, so passenger equals one ride request. I don't model any sort of longitudinal behavior of the passenger. It's just simple. And basically, I'm just going to model the passengers as entering if if their reservation value exceeds the current price in the system. Okay. So to model that, I think of every ride request as being drawn IID from some valuation distribution. And if the value that's drawn is bigger than the current price they enter, there's some exogenous rate of what I'll call app opens. Chris talked about the same thing, and that's basically like I open the app and look to see, do I want to request a ride? And then look at the price and determine whether I actually request a ride. So from that, it's pretty easy to work out, based on the pricing formula, what is the rate of ride requests. It's the exogenous rate times the tail probability that the valuation exceeds the current price. Okay, so this F bar is the tail CDF of the valuation distribution. Right, so that's the passengers. That's relatively simple. The drivers, I think, is where it gets a little bit more interesting. And this is maybe the one place where our motivation for choosing this model kind of came from what seemed to us to be like a natural distinction between drivers and passengers. I would say that I think of this as kind of a stylized extreme point, and there, especially as the platforms change the technology that they use to induce drivers to enter or exit, I think this can get a lot more interesting. But let me tell you what this is. Basically, the point that we make here is that we think of drivers as making decisions on just a substantively different time scale than passengers. Okay? So if a driver is thinking about whether to drive, for example, in the early days of Lyft, you had like a booking calendar when you would essentially say like when you wanted to be on or off the platform. And the time interval over which you were choosing to drive or not is probably something on the order of hours. And so essentially what we do is we say, well, kind of from a driver's perspective, they're not responding to the instantaneous state of the system. Instead, what they're thinking is, if I enter, what's the expected earnings that I'll receive if I'm part of the platform? And what they do is they compare the expected earnings they'll make while they're in the system to essentially the expected, kind of a reservation earnings that they want, a reservation earnings rate. Okay, this is also really interesting. So this is kind of a target earning model of the driver. Like basically, they have some fixed mental model of how much they want to be able to make, and they enter if it exceeds that. I think Chris pointed to examples of a lot of different driver behavior in their data, and you would certainly see that across all the platforms. So I think that's a really interesting direction. Also, first of all, just do you have the right kind of utility model for drivers? I think this is when I say that we're taking an extreme point. What I mean is this timescale separation between drivers and passengers is a fundamental part of the model. It would be interesting to think about what starts happening if drivers are responding more directly to instantaneous state. And in particular, I think the way this comes together with the network's comment earlier is if I'm able to provide signals to drivers that say, this is a place where I think demand is locally higher than supply. And what I'm doing is I want to induce drivers to move in that direction. And what I'm trading off, the effects I'm trading off are that it takes drivers time to move to a new area. It takes drivers away from the area that they were in. So I think that's really where the network modeling gets especially interesting. So that's kind of one of the things that we want to keep doing with this work. As with the passengers, I'm going to model this reservation earnings rate as IID across the drivers. So similarly, you can work out what is the actual rate at which drivers enter. There's some exogenous rate. Drivers will enter if their earnings, desired kind of reservation earnings rate is lower than what they think they're going to make in, per unit time. And it's expected earnings divided by expected time. Okay. You don't have to worry too much about the fact that the expecteds are both in numerator and denominator here. There's sort of a Wald's identity argument that lets you do away with that. Yeah.
On the rider model, it looked like
on the passenger model, yeah.
Yeah, it looks like they're not looking at the wait time. So is the way to think about your model that there are always available drivers?
No. Oh, yeah, sorry. That's a great point. So you're right. This is not the number of rides that actually get served. This is the number of ride requests. And so what will happen is that if there's no driver there, your ride request will be blocked, and it'll be dropped.
No, but what I mean is my decision as to whether or not to even make the request, that might depend on
the number of available drivers. Yeah. Yeah, so that's a really good point. So first of all, when I said earlier that I wasn't dealing with ETA, that's what I meant, that I'm not modeling. So in queuing models where you think about, and this is not necessarily something specific to me. I'd say that this type of trade-off exists everywhere. Let's just think about so I'm using a model where essentially the passenger's cost is blocking, right? They may not get served. Well, in a real queuing system, blocking and delay are not completely dissimilar from each other in the sense that if I get blocked, what that really is saying is I just have to wait longer to get done with whatever I want to get done, right? And so I think there's two ways you can think about blocking. It's actually what the cost is. It's I tried to get a ride and I couldn't, say New Year's Eve. Or you can think about it as I didn't get the ride and that means I have to wait longer to be able to get a ride. And I think of this as a very, very coarse sort of zeroth order approximation to the right thing to do. And the right thing to do would be to actually include ETAs in the model and model that. Yeah. Yeah, that's a good question. OK. So that's the drivers. So let me just quickly run through what the queuing model is. Basically, the queuing model is now, when I mean my queuing model, is in describing this to you, I'm not going to say anything about why drivers and passengers are coming in at the rates that they're coming in. They just are. So I've already told you that I have some model that's strategic for how I'll determine the rate at which rides are requested, how I'll determine the rate at which drivers actually enter the system. Now let me tell you sort of what actually happens inside the model with those rates of arrival of drivers and passengers. So basically, drivers enter at some rate lambda, and when there's a drivers available, ride requests arrive at some rate, which depends on the number of available drivers. That's what we computed earlier. If a driver is available, the ride is served, otherwise it's blocked. Rides last an exponential time with mean tau. In the network model, this sort of involves a random walk around the network, so it's a little more complicated than that. And after ride completions, this is another point where I think someone could do something interesting with this. So after ride completion, there's some exogenous probability that the driver signs out or becomes available. Okay? So another thing that could be interesting that you could do here is make the exit probability dependent on their experience in the system. For obvious reasons, that leads to a much more complicated game, so this is a far simplified version of that. I would say that I'm actually less sort of concerned about this assumption that this is exogenous, because drivers are still making entry decisions based on their kind of expected earnings in the platform. So it's not as if they're completely ignoring how they're going to do. But I think if you wanted to refine it a bit, you could think about making this something which is endogenous. Okay, so that's basically the model of what's going on. And so if you look at the picture of what's happening here, there's two reasons that there's available drivers. There's either new entry from the outside world, or there's a driver who was busy, who became available and came back into the system, who chose not to exit. Okay, so there's some queue that's going up and down, available drivers coming in, and then when rides are requested, this queue gets served down. Okay, so a major sort of simplification for us, and one of the reasons for exactly the lining up the assumptions we had, is that this type of queuing model turns out to be what's called a Jackson network, and this is more generally true for the network model. And Jackson networks are great because their steady-state distribution is a product. Right? So despite the fact that there's all these dependencies in the queuing network, the steady-state distribution has the property that in steady state, the queue lengths in the different parts of the network look like they're independent. Okay? So in particular here, what it means is that the number of available drivers is something which we have like an exact expression for the steady-state distribution. Okay, so I'll skip this slide. Sorry, I won't go through everything in detail. What I mean is, I just want to tell you what an equilibrium of our system is. So an equilibrium of our system involves basically saying, I need to connect together the strategic behavior of the passengers and drivers, the pricing policy, and the queuing model. And so what I do is I say, okay, let me take the queuing model, compute a steady-state distribution from it. Using the steady-state distribution, for every driver, I can work out what is their expected earnings that they'll make while they're in the system and what's the expected time they're going to live. I can use that to then work out what's the entry rate of drivers. And then for every passenger, I can work out, sort of, for the passenger, kind of the steady-state condition is easy. It's the same one we had before, that passengers will enter as long as the price is going to be lower than their reservation value, and that gives me the entry rate of ride requests. So all this comes back together again, and I need a consistency check that the steady-state distribution actually came from these things that I just computed. Right? So you can do that, and that's kind of a definition of a system equilibrium in our model. What we show is that basically, as long as you have very mild regularity conditions on the system, namely, among other things, that the price increases when the number of available drivers decreases. So this is a condition on the pricing function. Then equilibria always exist, and they're unique under reasonable sort of smoothness conditions. So I'll ignore what that is. So let me talk about, sorry, when I say smoothness conditions here, I mean on the distributions. Okay. So let me sort of move on to how we want to use this. So I guess, half the talk is like, here's a model that sort of sits on some knife edge of tractability and still capturing a bunch of effects that are important. I've already pointed out to you at least 5 or 6 different ways that I think you would want to do things to the model to capture effects that are important in practice. That said, at least in our experience thinking about it, adding any one of those things made the model much harder to work with. So in order to make progress beyond what we had, I think part of the question is going to be, where you get technical simplicity despite having added in these additional complications. And I think one thing for us, even with the model that we had, that is very helpful is to use asymptotics to simplify the analysis. This is something which is by now very standard in analyzing these types of matching markets. Eric Budish and Eduardo Azevedo have a really nice paper that sort of talks about some of the things that you can do using this type of approach. So in our case, the limiting approach that we use is that we have a sequence of systems we consider. In the nth system, I'm basically scaling up the exogenous rates, the arrival rates of passengers and of drivers. And in the nth system, I have some pricing policy that's actually indexed by n. Okay, and I'll talk to you a little bit about how that works. So in each system, this gives rise to a system equilibrium. And we basically analyze pricing by looking at the asymptotics of these equilibria. Okay, so that's what I'm going to show you. I'll show you a bunch of pictures that explain what's going on, and there's corresponding theorems behind it. Okay, so let me start with static pricing. Again, static pricing doesn't mean there's a single multiplier the whole day. It means that I have sort of predictable uncertainty on the order of hours or something like that I use to set a multiplier, but I don't change the multiplier on the basis of the exact number of available drivers that are in the system. So what you should be thinking when I say static is that idiosyncratic stochastic fluctuations are not being captured by the dynamic pricing policy. Okay? And so in math, this means that P of A is a constant for all A, that no matter what the level of the Q is, I'm setting the same multiplier. So there's a theorem here that, don't worry about reading the technical sort of expressions carefully. But here's basically what's going on. What it says is that you pick the multiplier that you're going to use at all A. Okay? Once you've done that, then if I scale, this should be scaled by n This should be Rn over n. It's a scaled completed rides. Obviously, the rate of completed rides is going to go to infinity if n goes to infinity. It's the scaled rate of completed rides that's normalized. So if I take Rn over n, the rate of completed rides divided by n, that has a really natural sort of interpretation. Imagine sort of two unconstrained systems. One in which, as a passenger, whenever I request a ride, there's always a driver waiting for me, all right? And another in which, as a driver, whenever I finish driving, there's always a passenger right there requesting a ride that I can get matched to, okay? So in one of them, demand is not in the first system I just described, supply is not a constraint. The second one, demand is not a constraint. So each of these two sort of naturally give you a supply curve and a demand curve. This expression is basically how many drivers would enter if they knew that whenever they were available, there would be a passenger immediately there for them. And this expression is how many passengers would enter if they knew that whenever they requested a ride, there would immediately be a driver there to serve them. That's the same entry rate we had before. And so that throughput is basically available. The throughput is a min of available supply and available demand. So that's really nice because you can visualize it as sort of a demand and supply curve crossing each other. This green curve here is the demand curve. This green curve here is the supply curve. They cross right at this point. Now, what's the x-axis? This is different than a usual plot in economics. The x-axis here is price. The y-axis is throughput. So I'll tell you about the red curves in a second. So what I'm saying here is that you pick a multiplier on the x-axis, and the actual throughput that you're going to see in the system is the minimum of this green curve and this green curve. Okay, so this sort of pyramid-shaped thing is what the overall throughput is as you vary the multiplier. And you can see that if your only choice was what multiplier to pick and you didn't have any dynamic pricing available, the multiplier you would pick is the one where they intersect, right? That's the peak. And so that's what we're going to call that the balanced price for the rest of the talk. The red curves are just depicting what happens as n increases, right? So these are simulations for finite n, and the green is the theory in the limiting system. Okay. All right, everybody okay with that? So basically what I'm saying is that there's like a natural notion of available supply and available demand, and I can use that to say that if what I want to do is maximize throughput, then the multiplier I would pick is the one that balances the two of them. It's pretty intuitive. It's just nice to get that out of the primitives. So I'll skip this slide. I just said that. So now let's talk about dynamic pricing. And what we did is we decided to focus on a particular family of dynamic pricing policies. There's a small part of the paper that says something on slightly more complex policies, but it's actually it is actually a little bit harder to deal with sort of arbitrary dynamic pricing policies and come up with exactly the same conclusions. So what we do is we focus on threshold policies, and these are very natural because they match exactly what's done in practice, which is basically that I have a threshold, and then if the number of available drivers drops below that threshold, I set up a multiplier that's a high multiplier. If the number of available drivers goes above that threshold, I set a multiplier that's a low multiplier. Okay, so I'm kind of moving between these two multipliers. The slightly more general thing we looked at is a finite number of thresholds. Okay, and then the more general thing obviously would be that the price curve can be anything across the number of available drivers. Right, so this is kind of inspired. The reason we specifically focused on this is because we wanted to try to say something about what surge and primetime policies are actually doing. And they basically have this flavor that there's kind of thresholds that when they're crossed, the multiplier is going to go up or down as a result. Okay, so I think I can convey kind of what our theorem is with pictures more easily than the result. I'll show you in a second. So let me just sort of parse this picture for you. Okay. So on the x-axis, on the x-axis, what I'm plotting again is the multiplier, right? So it's going from 0 up to 5 here. That's the price multiplier that I'm going to use. The blue curve is the throughput that I obtain if I just set that multiplier regardless of the number of available drivers. Same basically as the curves I was showing you in the previous graph, which is pure static pricing. Okay, the purple curve is what I get with a very particular dynamic pricing policy. The dynamic pricing policy is one where one of the two multipliers is set at green at this point right here, and the other multiplier is the one that's varying on the x-axis. Okay, now what does that mean? If I'm on this side, then what it means is that the high multiplier is this value, and the low multiplier is down here. And if I'm on this side, it means that the low multiplier is this value, and high multiplier is the one on this axis. Does that make sense? Okay, so that's kind of how you can do a 1D visualization of a family of dynamic pricing policies in this graph. And that's also why there's a kink right here. Okay, so this then, the purple curve, is the throughput that I get with that particular dynamic pricing policy as I vary on the x-axis. Okay. And what I'll do is I'll just make n larger, And as n gets larger, what you notice is, what you should see is that the static curve and the dynamic curve, the peaks are going to come together. Okay? And so that's what happens in the limit here. So this is the limiting value with n going to infinity. The purple curve is what I get from dynamic pricing, again, defined the way that I talked about it, where this is one of the two prices, and the other price is varying on the x-axis. And the blue curve is the one I just showed you a few minutes ago, which is what I get from static pricing. And what's the important point to notice from this graph is that both of them coincide at their peak. Okay? So what that's basically saying is that in the fluid limit, in this kind of hydrodynamic limit where we're scaling down by n, that you're not getting anything by using a dynamic pricing policy over a static pricing policy. Now, there's a bunch suppressed in these graphs. Okay, number one, it's numeric. So obviously, I haven't convinced you about other potential values for prices that I could use. Number two, I didn't say anything about the threshold, right? So like, what's going on with the threshold? And so I'll show you the theorem in a second. One of the things we're doing in the background here is that as n is getting larger, we're varying the threshold that we use. And we're doing so in an optimal way, given the two prices that are chosen. Right? So we're kind of favorably biasing the dynamic pricing policy to pick the best threshold that we could, given the two prices that were used. And so really the result is saying here is feel free to pick the threshold and the two prices however you want, and you're never going to do better than what static pricing gets you. Yeah? Oh, okay. Yeah. Now I should be done before that, since we were late already. Okay. So this is the limit. And what it basically says is, let Rn star be the rate of completed rides in the nth system using the optimal static price. And let Rn double star be the rate of completed rides in the nth system using the optimal threshold pricing strategy. Then if the valuation distribution has a monotone hazard rate, I'll talk more about this in a second, then the difference between these two scaled by n goes to 0. Okay? So some comments on this. First of all, I want to point out, so this is a really important restriction. In the result, in the proof of the result, what ends up happening is that we need to look at sort of how the level of demand changes as you vary the pricing policy. And it turns out that some condition on the valuation distribution is sort of necessary. It's a little bit looser than this. It doesn't quite have to be that strong, but that's probably the most interpretable definition. What's interesting is that there's no condition on the preferences of the drivers. FC does not enter into this theorem. So FC could be arbitrary. It's the restriction is only on FV. Okay, that's one point. The second point is, I guess what I find interesting about this result, the way I would state it, I think like the more glib statement is there's no value to dynamic pricing. I think the way I would state it that's a bit more precise is that there's only second order benefit to dynamic pricing. Right? So to the extent that you see benefits from dynamic pricing, it's happening because you're actually able to sort of correct things in the sort of the Gaussian term, not in the fluid term. The third comment I want to make is that maybe one naive view you might have on this result is, well, of course, because you took the limit, you got rid of all stochasticity. But the thing is that's not true. So the drivers, there is actually a well-defined steady state distribution that's seen, sorry, not drivers, by passengers when they enter, even in the limiting system. Okay, so when a passenger arrives, it is the case that the number of available drivers that they see is a random variable. And that remains true even when you pass to the limit. Okay, so it is true that we're speeding up the system, but from a passenger's perspective, they're always reacting to instantaneous state. So that stochasticity is still relevant. And I think that's part of what makes the fact that this happens a little bit surprising. So one comment I want to make is that these types of results are similar to stuff that's kind of longstanding in the revenue management literature, where in the early results in that literature, it was established that fluid pricing policies of the sort that we were talking about are not going to be better than dynamic pricing. And there's been a lot of work extending those types of results. But one interesting thing in that literature is there's not really been any work that looks at two-sided markets. So in that literature, usually what happens is you're kind of given a fixed basket of stuff to sell. And then you're allowed to use whatever mechanism you want to sell up to a deadline. And like the canonical example is airline tickets. So you're an airline, you're selling seats. And so you have like planes that are empty, and you have a bunch of seats to sell up to a deadline when the plane actually takes off. You're allowed to use whatever pricing policy you want to set prices for the seats. Okay? In our case, kind of one of the things I think that makes this really interesting is that we have this, the seats are strategic. The seats are the drivers, and they're entering because of what we're doing. So that's one of the big differences. And so again, just to point out kind of why this is interesting to work on is, I think if you look at the problems that are faced by many platforms in managing inventory internally, so the analog in Airbnb would be sort of managing the inventory of hotel rooms. They look like classic revenue management problems, but with strategic supply. And so that that perspective is something which opens up, I think, a range of algorithmic insight that isn't there yet in the literature. So I'm going to skip the proof just because we're already well over time with this session. I'm happy to talk to you about that offline if you want. Or if you play back the video and look at the slides slowly, you should be able to make it out. So last thing I'll tell you is, and this result I think is less surprising. It's just I just like it because of the nature of how we formulated it. So dynamic pricing is obviously helpful, right? And already there's a hint in this second order effect that I mentioned. And really, like, why do we use it? Well, one reason we use it is because we don't want to have to sit and futz around with what we think the system parameters are actually going to be, even when it's predictable uncertainty, all right? So one thing that's nice about dynamic pricing is it sort of naturally adjusts itself to wherever the system is living, okay? And somehow you would like to be able to make a statement that captures that robustness, that if the system parameters are known, yeah, then maybe static pricing is at least as good as doing as good as dynamic pricing. But when system parameters are unknown, presumably you should gain something in robustness because you were using a dynamic pricing policy. So there are a lot of different ways to give these kinds of robustness results. And again, in the revenue management literature, it usually involves taking the second order limit, like looking at a diffusion limit of the system. And those are nice, but definitely technically complex. What we want to do is take maybe more of a robust optimization viewpoint, where we basically said, let's ask, can we get sort of dynamic pricing to be near optimal across a wide range of system parameters? Okay. So again, I'll just tell you the result in pictures. So here what I'm doing is I'm picking one of the parameters, let's say the exogenous arrival rate of passengers and of app opens. And what I'm plotting here is this is the throughput I would get if, regardless of what for each value of the system parameter, I set the optimal static price. Okay. This is the blue curve is what I get if I set the optimal static price believing that the exogenous rate of customer arrivals was 4.0, but in fact it ended up being something different. And so yeah, right here obviously it's optimal, but then it really degrades quickly as I move away. Right? What you really want to look is the difference between these two things. Now suppose that what I tell myself is, okay, I don't know what mu0 is going to be exactly, but I think it's going to be between 3.6 and 4.4. So let me take each of those two, compute the corresponding static prices for each of those two, the optimal static prices, and use these two as the two prices in a dynamic pricing scheme. Okay? Again, buried in the background is what threshold do I set to move between these two. And I'll just tell you that we're using the same sort of optimality result that was in the proof to be able to set that threshold between. Once you give me the two prices, I can set the optimal threshold. Okay? And what you find is that if you now plot how dynamic pricing does using these two prices, the two prices from the extremes, then yeah, it degrades badly outside of that uncertainty set. But inside the uncertainty set, what we can show is that dynamic pricing always gets you at least the linear interpolation between these two optimal values. Okay? And at least in the numerical experiments we've done, that tends to be quite good. The green curve is concave in all the experiments we've looked at so far, numerical experiments. So basically the point is the result we have is something which characterizes the robustness of dynamic pricing through this notion of an uncertainty set over system parameters, and says that you always do at least as well as the linear interpolation from the endpoints of your uncertainty set. And this is kind of the technical statement of that. Okay, so let me conclude. A bunch of different things that we were trying to do in this work, and so some things I didn't manage to get to. Network modeling with multiple regions. When I say our main insights generalize, I mean they generalize sort of to the extent that we're able to characterize this difference between static and dynamic pricing. We haven't accounted for ETAs sort of in the way that David asked about. Right? Aggregate welfare is something, like I said, numerically we get very similar insights, but we're trying to work the theory out there. And I think it really gets interesting when you start changing, when you start asking, much more foundational design questions. So one thing that I think Chris even pointed out is that, you can imagine showing drivers these heat maps where we're saying, like, here is a place where there's more or less demand available. We have some model inside the queuing model. We've come up with some nice sort of tractable ways to deal with this. But extending it then to add in the strategic component has not been so easy. But I think that, again, this is a really important direction to take the work. Fee structure, changing the percentage we talked about already. And finally, I think the sort of changing the matching algorithm is something which is really not discussed a lot. If you ask Uber or Lyft, I'm sure they would say that they want it to be fairly transparent, so you're matched to the nearest driver. There's all kinds of really good reasons why you might want to manage inventory very differently across the network, especially if you, for those of you that were here for the reverse field trip day, they were talking about this sort of tessellation of the Earth into smaller regions than what they've been using before. Well, once you start doing that, I absolutely think you would want your match algorithm to occasionally pick people from adjacent regions, depending on, or another example of this would be that Chris on Monday mentioned that Uber wants to be able to accommodate driver preferences. It was either Chris or last week that if a driver says, hey, I want to be able to get back to the East Bay in an hour, I want to accommodate that. Well, that's going to change the match algorithm. You're not going to give it to the nearest driver necessarily. And I think this is, again, one of these things with sort of geographic matching. You would have to have a good queuing model, and you would have to be able to model the incentives of the participants reasonably well. So let me stop there. Thank you all for coming, and thank you to all the speakers again. So we're pretty well over time, so maybe if there's one or two questions, but otherwise we can wrap up here. Yeah, why don't we stop? Okay, thanks everyone.
A comment. I would like to thank the organizers for organizing this session.
Organizers would like to thank Costas for actually being the organizer.
Yeah, that's